Right now, in the tech world, a massive strategic maneuver is happening literally right under our noses. Welcome to this explainer, where we're going to completely deconstruct and decode a breathtaking play. We're looking at why an aerospace company, yes, a company known for building rockets, is completely bypassing the traditional global power grid to build what can only be described as a civilization-scale AI engine. I mean, the scale of this is truly unprecedented, and as you'll see, the underlying economics are quietly shifting the entire foundation of the artificial intelligence industry. Let's kick things off with a number that is just, well, it's mind-boggling. $15.8 billion. That's the amount of capital expenditure, which is really just hard cash spent on physical infrastructure, being poured into AI in a single quarter. To put that massive number into perspective for you, that is more than double their total recent quarterly revenue of $7.8 billion. When a company is willing to gamble over 200% of its quarterly revenue on a single infrastructure play, it begs a massive question, right? Why? What exactly is the endgame that justifies betting the entire house? To understand what $15.8 billion actually buys, we really have to grasp the sheer physical scale of a 10-gigawatt ambition. If you look at the slide here, compare that tiny black square on the far left. That's a standard 50 to 100 megawatt AI data center. To the second box, which represents a single next-generation 1.4 gigawatt nuclear reactor, the third box, that's the equivalent of 7 of those nuclear reactors combined. And finally, that massive blue grid on the right represents the entire peak summer power demand of New York City. That is exactly what 10 gigawatts is. So we're not talking about your standard IT procurement ordering a few servers here. This is civilization-level infrastructure spanning multiple continental sites. Okay, so here is our playbook for decoding all of this today. First, the 10-gigawatt ambition. Second, grid bypassing. Third, the new master metric. Fourth, time arbitrage. And finally, high-margin tokens. Let's dive right into part one, the 10-gigawatt ambition. Check out this detailed schematic. It pieces together a complete ecosystem, mapping explosive compute demand directly against on-site power generation. On the left side, the compute core houses over 100,000 H100 equivalents, literally some of the most powerful processors on Earth. But follow the pipes to the right, to that power generation hub. They're integrating high-efficiency gas cycle turbines directly on-site to provide that massive 10-gigawatt capacity. And the specific data points on the right, that's where the true genius is revealed. By generating power locally, they drop their energy costs to just 4 cents per kilowatt hour. That drives a highly targeted 15% return on investment and captures a projected 25% market share in global compute. Plus, this localized cycle creates a massive 30% efficiency gain. They aren't just spending a $15.8 billion quarterly budget. This scales up to a highly calculated $50 billion total CapEx plan designed to lock in global AI leadership. Moving on to part two, bypassing the grid bottleneck. Having a 10-gigawatt ambition means absolutely nothing if you can't actually plug it in. Look at this slide. On the left is the traditional bottleneck, a transmission tower locked in grid dependency. Trying to get utility power today basically means drowning in permits, waiting on aging infrastructure, and suffering years of delays. But on the right is the brute force alternative. Instead of waiting years, they're deploying highly organized rows of on-site gas turbines. The timeline here shows a staggering acceleration, scaling from 27 turbines in February to 69 turbines by July, reaching over 1.2 gigawatts. And that benchmark at the bottom right, that's the ultimate flex, 300 megawatts deployed in exactly 122 days. They are entirely bypassing the grid to achieve unprecedented speed. Let's compare these paradigms directly. Traditional hyperscalers are stuck with agonizing 2 to 4 year lead times. And for that long wait, they charge a standard cost plus lease of around $12 million per megawatt, which is essentially just passing the raw cost of the building onto the customer with a small, safe margin. But look at the vertical integration model. By utilizing those on-site gas turbines, lead times plummet to an astonishing 3 to 5 months. And because they can offer that kind of breakneck speed, they pivot entirely to a value-based premium pricing model. They can command a massive $30 million to $50 million per megawatt simply because they are the only ones who can turn the lights on today. All right, part three, the new master metric. So why on earth would any rational buyer willingly pay a 3x to 4x premium just for early infrastructure? Well, the answer lies in the new techno-economic equation of AI. Notice how the old paradigm on the left, peak flops per GPU, is completely crossed out? That basically just measured how fast a raw silicon chip could do basic math. The new paradigm on the right features a gauge pushed entirely into the red line. The new master metric is TPS/MW, or tokens per second per megawatt. Power is now the ultimate bottleneck. The winner here is the operator who can squeeze the absolute highest volume of monetizable tokens out of a strictly capped 1 megawatt power footprint. And as that bottom text reveals, new architectural leaps like the NVIDIA GB300 and VL72 are exactly what allow operators to push up to 5 times higher token throughput within that exact same strict power envelope.
Let's walk through the flowchart we have here, because this creates a direct life cycle evaluation. Starting on the far left, you have a strictly capped raw input of just 1 megawatt of power. That power flows into the processing box housing those hyper-efficient GPU clusters. The cluster then outputs that crucial new metric we just talked about, TPS/MW. Finally, that efficiency directly converts into the last box on the right, monetization through API and app revenue. Simply put, this means charging developers and users every single time an AI answers a prompt, writes a line of code, or generates an image. It is a direct pipeline converting raw electrical energy into incredibly lucrative digital tokens.
Which brings us to part 4, the time arbitrage premium. This right here is the absolute core of the whole strategy we're unpacking in this explainer. It turns out they aren't actually selling compute at all. Look at the 2 horizontal tracks on this timeline. The bottom track represents traditional grid-dependent competitors who won't get their systems fully online until year 2. But the top orange track represents the brute force on-site generation strategy coming online at just month 4. See that massive green shaded area filling the space between month 4 and year 2? That's labeled the time premium window. This empty space on the calendar is the actual product being sold. In the AI arms race, if your competitor releases a next-generation model a year ahead of you, they capture the entire global market, lock in the enterprise contracts, and dictate the apps we use every day. In this space, time literally equals billions of dollars.
So by leveraging brute force engineering to launch earlier than anyone else, they capture that massive blue area on this value capture curve, the time arbitrage premium. The text boxes call out the specific insights here. It's an eye-watering $100 billion annual metric. In a market where early access generates that kind of staggering revenue, a 3 to 5 month head start completely dwarfs any potential savings a company might get by waiting for cheaper traditional construction costs. Actually, let's just make it clear. The product isn't the silicon. The product is time.
And finally, part 5, printing high-margin tokens.
Take a look at the visual here to see the financial math of the buyer because it shows why acquiring this early access is an absolute no-brainer. You see that orange pipeline feeding just 1 gigawatt of raw power input directly into a block of GB300 GPU clusters. Now look at what happens on top. It acts as a literal digital money printer. The text confirms the staggering revenue potential greater than $100 billion in annual API revenue. When raw electrical power is converted directly into saleable tokens at this unprecedented scale, it completely changes a company's fundamental valuation on Wall Street. The economics become totally unhinged from standard IT procurement.
Walk through the math on this pricing stack with me. The bottom gray block is the standard $12 million lease you'd pay if you wanted to wait years. The orange block in the middle is that massive $30 to $50 million premium charged for unparalleled speed. Now look at the towering green pillar on top. That is the greater than $100 million in API revenue potential for the buyer on just a single megawatt. Because that green pillar is so massively disproportionate to the cost below it, the bracket on the right highlights a crucial financial metric, a hyper-fast sub-1-year payback period. The buyer will gladly absorb a 4x infrastructure premium for sure because the absolute scale of the revenue makes the deal instantly profitable.
To pull everything from this explainer together, take a look at this flywheel. It shows the continuous loop defining this new era. Starting with the orange gear, you aggressively acquire time and power by brute forcing on-site generation, shaving years off deployment. That turns the gray gear, applying a strategic premium. You're charging a massive $31 to $48 million premium per megawatt to big tech labs who simply cannot afford a $100 million a year delay, which finally turns the blue gear, letting those clients run continuous workloads and print high-margin tokens, transforming early megawatt access into unprecedented cash flow.
So we've seen how the old metrics of raw chips and peak flops have been entirely replaced. The real product of the modern AI era is the physical power and the severely compressed time required to run these models before anyone else. So, I want to leave you with this final thought based on what we've explored today. If that is true, then who actually holds the keys to our AI future? Is it the software developers writing the code? Or the engineers who can build the fastest power plant?